Hello, my name is Oleksandr Dolhanenko, and today I'll be presenting our paper, Intelligent System for Diabetes Management on Mobile Devices. Diabetes is growing fast. The number of people living with it has more than quadrupled since 1990. Also, recently, we see an increase in diabetes threat in Ukraine as a result of stress due to the war. Without proper control, diabetes can lead to serious complications like heart disease or even blindness. Of course, there are solutions on the market. CGM devices, or continuous glucose monitors, help track glucose levels, which allows users to react to glucose spikes. Predicting these spikes in advance is challenging, as they are depending on meal intake, physical activity, insulin intake, etc. So the existing solutions are very restricted. They're slow to update, they don't give away their data, and often use outdated and primitive glucose prediction models, if any. Today's smartphones are powerful enough to run machine learning locally. They also collect health data passively. This creates a perfect opportunity to bring smart, personalized glucose prediction to the devices we already carry every day. Our end goal is to predict blood glucose levels accurately and in a personalized manner by using historical data, analyzing time-based patterns, and taking into account meal and insulin logs. The system currently runs on Android, adapts over time, and empowers people to act before the problems arise. At the heart of any AI-powered system is data. Our application connects to CGM apps like Jgluco and Xdrip. It reads glucose every 5 minutes, builds local history, and stores it securely. The modular design allows us to support various sensors and various third-party applications. Typically, sensors record glucose readings every 5 minutes, in some cases every minute, resulting in up to 1,440 data points per day for a single user. Of course, data gaps are expected. For example, the smartphone is left behind or the Bluetooth signal becomes unstable. And we use methods like linear interpolation to fill in the gaps. Let's talk about glucose level prediction. Traditional models like ARIMA are limited. They don't capture non-linear personalized patterns. But LSTM neural networks, on the other hand, learn long-term trends and adapt to individual metabolic responses, making them ideal for glucose prediction. On the slide here, you can see our current version of the neural network architecture. It currently only supports glucose history inputs, but we're actively working on adding new input features. At the core, we have the LSTM layer, which, as I mentioned, is great at remembering long-term trends. Our carrier is TensorFlow. We train personalized neural network models for every user on a daily basis. That model then gets exported into the light format and runs on device. We're also looking into moving the entire personalization and training process on device in the future. As mentioned before, glucose levels depend on multiple factors. Our system is designed with a modular architecture and will allow us to add more data sources for our model training and inference. We are integrating Google Health Connect to get access to sleep data, physical activity data, heart rate and stress levels, but more importantly, we're designing a meal logging system that will use natural language processing. We will enrich the recordings using LLMs, and this will allow us to automatically suggest meal intake logs. If approved by the user, they will play part in model training and inference. Here is the current state of our mobile application interface. We display the glucose chart with predictions. We support both Jgluco and Xdrip. We also allow parents to monitor their children's glucose levels remotely, or think of a patient and doctor. All user data is backed up securely in the cloud, and the personalized prediction models are downloaded on a daily basis. This allowed us to run 3 stages of our experiment. Our goal was to evaluate the data flow and neural network model performance. This is a critical step before we start our clinical trials. This will help us understand if our system and model architecture are robust enough to scale. Our experiment lasted 6 weeks in total. We tested combinations of CGM sensors and reader applications. In general, our data flow measurements are interpreted as successful, given some data loss was expected due to system background execution restrictions and dose mode in Android. As we were training the personalized neural network daily, we did see model accuracy improvements compared to a generalized model. As a result, we've developed the core of our AI-driven health data aggregator solution. This solution currently works with glucose data, and our prediction model will expand to support additional features such as sleep patterns, exercise, meal intake logging using NLP, and others. As of the current model architecture, we see clear performance improvements over general models, and we are planning on using this version for our upcoming open testing with real patients. Of course, we are also planning on going cross-platform and supporting iOS in the future. Smartphones and neural networks are reshaping diabetes care. By predicting glucose levels, we give patients more control, and having algorithms tailored specifically to the user makes those predictions much more accurate. With natural language processing, meal logging, sleep pattern analysis, and more data streams, we're on track for open testing with real patients to gather as much data as possible to continuously refine our models. That is all. Thank you for your attention.